A single teaspoon of a neutron star would weigh billions of tons on Earth. These cosmic remnants are nature's most extreme laboratories, and we are about to uncover 25 wonders locked inside them. By the end of this journey, you will understand how these objects are rewriting the laws of physics, what strange states of matter could exist at their cores, and how do they warp the very fabric of space and time. Are you ready to see how much of our universe still defies explanation? Deep within that unimaginable density, the first wonder awaits. The heart of a neutron star is not a solid ball, but a neutron superfluid, a state of matter so alien it has no friction at all. Imagine a fluid that could never form a single ripple, a substance that, once set in motion, would swirl forever. This is not magic, but the result of physics pushed past its breaking point. Under pressures billions of times greater than anything on Earth, the individual neutrons are forced to pair up, losing their identities to become one single quantum entity. This collective behavior is what allows them to flow without any resistance whatsoever. We cannot see this directly, of course, but its effects are written in the stars. Astronomers observe sudden, tiny speed-ups in the spin of pulsars, events known as glitches. The leading explanation is that this frictionless superfluid core, spinning just beneath the crust, suddenly transfers a massive amount of its energy outward, giving the entire star a measurable kick. This means we are indirectly sensing the dynamics of a quantum sea, a perfect fluid that challenges everything we know about how matter can behave. It reveals that in the most extreme environments, the universe operates on rules that are both profoundly strange and deeply elegant. This seemingly perfect sphere hides a landscape of unimaginable scale. The second wonder is the crust of the neutron star itself, a surface rippled with mountains. But these are not mountains as we know them. Formed as the star's incredibly rigid crust strains under immense magnetic forces and its own rapid spin, these imperfections are mere centimeters tall. Think of the gentle ripple on the surface of a pond, only forged from materials stronger than any substance we can create. Yet, despite their minuscule height, these crustal mountains possess the mass of entire Earth mountains. All that weight compressed into such a tiny bump creates a profound warp in the fabric of space-time around it. Just by studying the subtle influence of these microscopic mountains, astronomers can deduce the internal structure of the star and test the absolute limits of material strength in the cosmos. It is a stark reminder that even the most seemingly smooth and perfect objects can conceal entire worlds of intricate detail, sculpted by forces beyond our everyday experience. But the crushing reality of a neutron star's core does not stop with a sea of neutrons. As we venture deeper to pressures that dwarf even those found in the inner crust, we encounter the third wonder, a substance so bizarre it is known as Hyperon soup. Here, the neutrons themselves can no longer hold their familiar form. They are squeezed so violently that they begin to dissolve, breaking apart into their most fundamental building blocks, their constituent quarks. In this chaotic environment, new particles are forged, exotic entities known as hyperons. A hyperon is a strange baryon, a relative of the proton and neutron, but with a key difference. It contains at least one strange quark, a type of fundamental particle that is incredibly unstable and fleeting everywhere else in the universe. Only within the protective, immense pressure of a neutron star's heart can these hyperons exist in any stable form. Their creation fundamentally changes the character of the star's interior. This hyperon soup is softer and more compressible than a pure neutron fluid, altering the entire equation of state that governs the star. This single fact determines the ultimate fate of these cosmic objects, setting a limit on how massive a neutron star can become before it collapses into a black hole. The potential discovery of Hyperon signatures, perhaps through precise measurements of gravitational waves from colliding neutron stars, would be a monumental leap. It would confirm that these stars are not just neutron-packed orbs, but natural laboratories for particle physics, cauldrons of creation where we can observe the strong nuclear force operating in a regime no Earth-bound collider can ever replicate. This rhythmic pulse, a beacon in the dark, is the fourth wonder, the Pulsar Lighthouse mechanism. Not all neutron stars reveal themselves this way, only those with a precise cosmic alignment. Picture a star with a magnetic field trillions of times stronger than Earth's, a field so intense it is not aligned with the star's axis of spin. This misalignment is the key. As the star rotates, this tilted magnetic field acts like an immense cosmic engine, funneling charged particles at nearly the speed of light toward its magnetic poles. There, at these focal points, the particles release an incredible amount of energy, generating focused beams of radiation. These can be radio waves, X-rays, or even gamma rays, shooting out into space like the beam from a lighthouse. If the Earth happens to lie in the path of that sweeping beam, we detect a regular pulse with every rotation, a flash that can be as precise as an atomic clock. Some pulsars spin hundreds of times per second, their rhythm unwavering over decades. This incredible consistency transforms them into tools for cosmic navigation. Scientists have even proposed using networks of pulsars as a galactic positioning system for future spacecraft, a testament to their reliability. The lighthouse effect is more than a curious signal. It is a direct observation of fundamental forces, of magnetism and motion intertwining to create one of the universe's most persistent and recognizable heartbeats. That perfect, frictionless sea is not entirely still. Deep within the neutron superfluid, a storm of microscopic whirlpools perpetually spins. These are the fifth wonder, quantum vortices. Each one is a tiny tornado of swirling fluid, but unlike any whirlpool on Earth, these are governed by the strict rules of quantum mechanics. Each vortex carries one single, indivisible unit of angular momentum, a fundamental packet of spin. Billions upon billions of these threads are embedded in the superfluid, and they become pinned to the star's solid, crystalline crust. This creates a cosmic tug of war between the inner superfluid, which wants to spin freely, and the outer crust, which is slowing down over time. The drama of a pulsar glitch, that sudden speed up in spin, is likely the moment this delicate balance snaps. When a vast collection of these pinned vortices suddenly breaks free all at once, they rush outward, transferring a massive surge of rotational energy to the crust. In an instant, the entire star spins faster. This means that the tiny, quantum behavior of these infinitesimal whirlpools can literally change the rotation rate of an object weighing more than our Sun. It is one of the most stunning examples in the universe of how the rules of the quantum world do not just apply to atoms in a lab. They can scale up, governing the motion of entire stars and creating observable phenomena across the vastness of space. Beneath those minuscule mountains lies a skin of solid iron, the sixth wonder of these cosmic remnants. But this is no ordinary metal. The outermost layer of a neutron star is a crust forged in conditions that make the core of our Sun seem placid. Here, iron nuclei are not merely atoms, they are squeezed into an impossibly dense, rigid crystalline lattice. Picture a perfect, unyielding solid, but under pressures millions of times greater than anything found on Earth. This creates a material of almost unimaginable strength, a crust capable of supporting the star's entire landscape against a gravitational pull that would instantly crush any substance we know. Its rigidity is what allows it to strain and form those tiny, massive mountains, and to withstand the titanic forces trying to tear it apart from within. Within this iron lattice, another strange transformation occurs. The electrons are utterly stripped from their atomic nuclei and forced to move freely through the rigid structure, creating a superconductive sea. This flowing ocean of charged particles is a fundamental part of the star's engine, directly shaping and sustaining its immense magnetic field. The entire life of the star is influenced by this iron skin. It dictates how heat escapes from the fiery interior, controls the emission of radiation from the surface, and governs how the star interacts with any nearby companion or cloud of cosmic gas. This is material science pushed to the ultimate extreme, where a familiar element like iron becomes an utterly alien substance, defining the very character of one of the universe's most mysterious objects. Yet even the Hyperon soup may not be the final state of matter within a neutron star. At the very center of the most massive of these objects, the density soars to a point where even the structure of neutrons and hyperons breaks down completely. This is the seventh wonder, the potential existence of a quark-gluon plasma. Here, the neutrons themselves are crushed back into their most fundamental parts, dissolving into a seething ocean of free quarks and the gluons that bind them. This state of matter is not just exotic, it is primordial. It is the very same condition that filled the entire universe in the first fleeting moments after the Big Bang. For an instant at the beginning of time, everything was a quark-gluon plasma. Today, we can only recreate this state for a split second in our most powerful particle colliders. But a massive neutron star could be a natural, stable container for this primordial soup, a cosmic relic preserving the universe's earliest recipe. The presence of such a core would fundamentally change the star's character. This quark-gluon plasma is a softer, more compressible material than a fluid of intact neutrons. Its existence would make it impossible for the star to support itself beyond a certain mass, effectively setting the ultimate upper limit on how heavy a neutron star can become before it surrenders to gravity and forms a black hole. The search for evidence is ongoing. When two neutron stars spiral together and merge, the resulting cataclysm sends ripples through space-time itself. By carefully analyzing the gravitational waves from such an event, scientists hope to detect a signature in the signal that points to a soft quark matter core. This would be a discovery of profound significance. It would mean that the hearts of these distant stellar corpses are not just laboratories for exotic physics, but are also windows allowing us to peer directly back into the first microseconds of cosmic existence. These unimaginably powerful magnetic fields are the eighth wonder, a direct result of the star's violent birth. During the supernova collapse, the progenitor star's core is squeezed from a size larger than a city down to a sphere just a few miles across. Its pre-existing magnetic field is trapped within this collapsing matter, and as the core shrinks, the field lines are pulled inward and wound up with incredible force. This process, a cosmic dynamo, amplifies the magnetic field to intensities trillions of times stronger than Earth's own protective shield. We are speaking of forces so potent they can tear atoms apart from a distance of thousands of kilometers, ripping electrons from their orbits and reshaping the very vacuum of space around the star. This magnetic engine does more than just power the pulsar's lighthouse beam. It acts as a natural particle accelerator on a galactic scale, whipping electrons and protons along curved field lines until they reach velocities indistinguishable from the speed of light. When these ultra-relativistic particles are suddenly slowed or change direction, They release their immense kinetic energy as radiation, from brilliant X-rays to the most powerful gamma-ray bursts we can detect. The study of this dynamo effect is a cornerstone of modern astrophysics, a direct link between the death throes of a giant star and the creation of a long-lasting cosmic powerhouse. It demonstrates how a single, catastrophic event can forge an object that, for millennia afterward, continues to influence its surroundings with raw magnetic force, driving the energetic emissions we can observe from light years across the galaxy. These immense gravitational fields do more than just warp space, they can also set it ringing. The ninth wonder is the emission of gravitational waves from orbiting neutron stars. When two of these incredibly dense objects are locked in a mutual dance, their orbital motion creates ripples in the very fabric of space-time, waves of gravity that travel outward at the speed of light. This phenomenon, predicted by Einstein over a century ago, is a direct consequence of his theory of general relativity. As the stars circle one another, they lose orbital energy by radiating these gravitational ripples, causing them to spiral inward, drawing closer together with each passing orbit. This slow cosmic dance culminates in a final, violent merger, an event of cataclysmic power. For decades, this was purely theoretical, but on August 17, 2017, that changed forever. The LIGO and Virgo observatories detected gravitational waves from an event designated GW 170817, the collision of two neutron stars over 100 million light-years away. This was not just a detection, it was the opening of an entirely new window on the cosmos. The gravitational wave signal carried encoded information about the nature of the colliding objects, allowing scientists to probe the properties of neutron star matter in a way never before possible. It provided clues about their internal composition, their size, and the incredible strength of their material. This single event demonstrated that these distant, enigmatic objects are more than just cosmic curiosities. They are fundamental tools for discovery, natural laboratories where we can test the most extreme predictions of physics. They reveal that space-time is not a static stage, but a dynamic, living entity that can be stretched, squeezed, and set into motion by the most massive objects in the universe. From the steady heartbeat of a pulsar to the sudden, inexplicable flash, these objects are full of surprises. The 10th wonder is the mystery of fast radio bursts, colossal eruptions of energy that last for just a few thousandths of a second. In that fleeting instant, a single burst can release more energy than our sun emits over many days. The source of these cosmic firecrackers has been one of the biggest puzzles in modern astronomy, and the prime suspects are a special class of neutron stars known as magnetars. These are neutron stars with magnetic fields 1,000 times more powerful than ordinary pulsars, fields so strong they could strip the information from a credit card from 500,000 miles away. The leading theory suggests that these immense magnetic fields can literally crack the star's iron crust, causing a starquake. This sudden fracturing of the rigid surface unleashes a catastrophic release of pent-up magnetic energy, which then ripples outward as an intense, focused blast of radio waves. Other theories propose dramatic magnetic reconnection events, where field lines snap and realign in an explosive process. Whatever the precise trigger, the result is a signal so powerful it can travel across billions of light-years of empty space and still be detected by our radio telescopes here on Earth. This incredible journey actually makes these bursts useful tools for science. As the radio waves traverse the vast cosmic voids between galaxies, they are subtly altered by the sparse gas and plasma they encounter. By studying how the burst has been stretched and changed, astronomers can effectively map the invisible structure of the universe, weighing the missing matter between galaxies. Each new fast radio burst is another piece of a cosmic detective story, a clue pointing toward the most violent and energetic processes occurring in the hearts of these bizarre stellar remnants. Their very existence reminds us that for all we have learned, neutron stars still hold profound secrets, capable of unleashing forces we are only beginning to comprehend. But the solid iron skin is merely the outer shell of a much deeper mystery. As we journey beneath that unyielding crust, the pressure soars to even more staggering levels, giving rise to the 11th wonder, the realm of exotic nuclear ice. Here, the familiar rules of chemistry and structure have been utterly rewritten. The atomic nuclei, mostly neutrons, are squeezed so tightly together that they begin to organize themselves into bizarre, spaghetti-like strands. This is the first stage of what physicists call nuclear pasta, the competition between the powerful nuclear force, which tries to bind the nuclei together, and the immense electromagnetic repulsion, which tries to push them apart, results in these strange, elongated shapes. Deeper still, the pressure increases further, and these strands of spaghetti are forced to merge into flat sheets, a phase known as nuclear lasagna. And at the very deepest part of this layer, the pressure is so extreme that these sheets are compressed into dense, lumpy spheres like cosmic nuclei. This nuclear pasta is a state of matter that defies simple classification, being neither a true solid nor a conventional liquid, but something entirely its own. It is also thought to be the strongest material in the known universe, forming a rigid lattice far stronger than diamond or any substance we can create. This incredible strength means the nuclear pasta layer can support immense strain, and when it finally cracks under the stress, it could trigger a starquake, a violent rearrangement of the star's entire structure that releases more energy than 1,000 suns. The behavior of this exotic matter directly influences how the star spins and slows over millennia, leaving its subtle signature in the timing of the pulsar's rhythmic beat. By studying the theoretical properties of these pasta phases, scientists gain a crucial window into the fundamental forces that govern matter at densities far beyond our reach, revealing a hidden world of complex architecture flourishing in the heart of an otherwise brutally simple star. This cascade of creation begins with a single electron, whipped to near light speed by the pulsar's unimaginable magnetic field. As it is forced to spiral along a curved magnetic field line, it must shed energy, and it does so by emitting a gamma-ray photon, a particle of light with immense energy. This process, known as curvature radiation, is just the first step. The true wonder unfolds when that newly born gamma-ray photon, itself moving through the same intense magnetic field, spontaneously transforms. It vanishes, and in its place, a pair of new particles pops into existence, an electron and its antimatter counterpart, a positron. This is pair production, a direct conversion of pure energy into matter, a phenomenon predicted by Einstein that occurs naturally and constantly around these stars. This single event triggers an avalanche. Each new particle can itself be accelerated, radiate more gamma rays, and create more pairs, resulting in a dense, seething plasma of electrons and positrons that floods the magnetosphere. This is the very fuel that feeds the pulsar's powerful wind and shapes its intense radiation beams. We are witnessing a cosmic engine that runs on the most fundamental laws of quantum physics and relativity. Our most powerful particle colliders on Earth strive to recreate these conditions for a fraction of a second, but here, around a neutron star, it is a continuous, self-sustaining process. This synergy between the immense and the infinitesimal reveals how these distant objects are not just astronomical curiosities. They are fundamental bridges connecting the large-scale dynamics of stars to the quantum dance of particles, showing us how the universe itself can operate as the most powerful laboratory of all. Deep within every neutron star lies a single, unsolved equation. This is the 13th wonder, the equation of state, a mathematical key that unlocks the star's entire internal structure. It is not a simple formula, but a profound relationship describing how matter behaves when it is squeezed beyond all comprehension. It tells us how much the pressure will rise for a given increase in density, defining the very character of the star's heart. Is that core a sea of pure neutrons, a Hyperon soup, or a free-floating Quark-Gluon plasma? Each possibility has its own unique equation of state, its own signature. A star with a soft, compressible core of quark matter will be smaller and denser for a given mass, while a star with a stiff core of intact neutrons will be larger and more rigid. This single theoretical curve determines the ultimate limits of these cosmic objects, setting the maximum mass a neutron star can possibly bear before it collapses into a black hole. Yet this is not just a theoretical puzzle confined to blackboards. Astronomers are actively testing these equations against the stars themselves. By observing binary systems where two neutron stars orbit one another, they can measure their masses with incredible precision. They study how the immense gravity of one star distorts the shape of its partner, a phenomenon called tidal deformation, which reveals the star's stiffness and, by extension, its internal composition. Every new observation, every ripple in space-time from a neutron-star merger, adds another data point, another constraint that helps us rule out some theories and bring others into sharper focus. The quest to solve the equation of state is more than an academic exercise. It is a fundamental investigation into the nature of matter itself, pushing our knowledge of nuclear physics into a realm we can never recreate on Earth. It underscores that these distant, silent objects are the universe's most demanding examiners, constantly testing whether our deepest theories can survive their extreme reality. These cosmic clocks offer a rhythm so steady it can detect the faintest whispers of the universe. The 14th wonder is the Pulsar Timing Array, a network of these celestial metronomes used to listen for the subtle passage of gravitational waves. By monitoring the incredibly precise arrival times of radio pulses from a collection of pulsars scattered across our galaxy, astronomers have constructed an instrument of staggering scale. This is not a telescope made of metal and glass, but a galaxy-sized interferometer. The concept is profound in its elegance. As a low-frequency gravitational wave, perhaps from a distant pair of orbiting supermassive black holes, washes through our region of space, it does something remarkable. It very slightly stretches and squeezes the fabric of spacetime itself. This minuscule distortion changes the distance between Earth and the pulsars by a tiny amount, causing the rhythmic pulses to arrive just a little early or a little late. No single pulsar tells the whole story. It is the correlated pattern of these timing shifts across the entire array that reveals the presence of the wave. This method is uniquely sensitive to the gravitational wave background, the collective hum of all such events throughout the cosmos, a relic sea of ripples from countless mergers over billions of years. Listening to this hum allows us to probe the large-scale structure of the universe in a way light alone never could. It turns these spinning stellar remnants into the most sensitive microphones, eavesdropping on the deepest, most fundamental vibrations of reality and opening a completely new avenue for understanding the cosmos. The fading heat of a neutron star tells a story billions of years in the making. This is the 15th wonder, a slow and silent cooling process that encodes the star's deepest secrets. Born in the unimaginable inferno of a supernova, a new neutron star is a blistering trillion degrees, but it does not stay that way. It immediately begins a long journey toward the cold of deep space, shedding its immense thermal energy over millennia. How it cools, however, is far from simple. The star has two primary ways to lose its heat. The first is through the emission of neutrinos, those ghostly particles that barely interact with matter. These are generated in profound numbers deep within the core, where exotic processes allow them to carry energy away directly through the star's dense interior, unimpeded. The second method is the more familiar emission of photons or light from the star's blazing surface. For the first million years or so, the neutrino cooling dominates, a silent, internal energy drain that far outpaces the surface radiation. The exact rate of this cooling is not arbitrary. It acts as a direct thermometer for the star's heart. If the core is filled with a neutron superfluid, the cooling accelerates dramatically as the formation of these frictionless pairs releases a flood of neutrinos. If exotic particles like hyperons exist in the interior, they open up additional channels for neutrino emission, making the star cool even faster. By carefully observing the surface temperature of neutron stars of different ages, astronomers can trace out a cooling curve. A star that is cooler than predicted for its age is a powerful clue. It suggests the presence of these exotic components in its core, a direct glimpse into physics operating at densities we cannot replicate. This gradual loss of warmth is more than a slow fade to black. It is a cosmic diagnostic tool, a way to peer into the heart of these distant objects and read the hidden story of what they are made of, written in the language of fading heat. The space surrounding a neutron star is anything but empty. It is a seething, dynamic arena known as the Magnetosphere, the 16th wonder, a region completely dominated by the star's unimaginable magnetic field. Here, charged particles like electrons and positrons are not merely present, they are trapped and whipped to velocities indistinguishable from the speed of light. The shape of this entire domain is sculpted by a cosmic tug of war between the star's furious rotation and the orientation of its magnetic poles. If the magnetic axis is tilted, as it is in a pulsar, the entire magnetosphere spins like a furious top, creating gaps and sheets of electric current that crackle with energy. It is within these specific regions, these natural particle accelerators, that the intense radiation we observe is born. The pulsed emission, the steady heartbeat of a pulsar, is a direct signal from this structured chaos. A lighthouse beam generated as the stars spin sweeps this radiation across our line of sight. But the influence of the magnetosphere does not stop at the star's immediate vicinity. It powers a relentless, supersonic gale of particles flowing outward, a relativistic wind that slams into the surrounding interstellar gas. This collision creates some of the most beautiful and complex structures in the cosmos, pulsar wind nebulae. The famous Crab Nebula, with its intricate, glowing filaments, is a stellar tombstone illuminated entirely by the pulsar wind from the neutron star at its heart. To truly understand the violent physics of this magnetosphere, scientists must merge the laws of plasma physics, which govern the behavior of charged particles, with the mind-bending curvature of space described by general relativity. It is a frontier where the rules of electromagnetism and gravity intertwine, creating a laboratory for the most extreme physics just above the surface of one of the universe's most mysterious objects. Even the most rigid neutron star can be stretched by a gravitational embrace. When two of these cosmic orbs orbit one another, their immense gravity does more than just hold them in a mutual dance, it literally pulls on their shapes. This 17th wonder is tidal deformability, a subtle but powerful probe into the star's deepest nature. Each star raises a tidal bulge on its partner, much like the moon raises tides on our oceans, but here the forces are unimaginably greater. The true wonder lies not in the bulge itself, but in how easily it forms. A star with a soft, compressible core, perhaps one filled with free quarks, will deform very easily, creating a large tidal bulge. A star with a stiff, rigid interior of nuclear pasta will strongly resist this pull, remaining almost perfectly spherical. This single property, the star's squishiness, is a direct readout of its internal composition and its fundamental equation of state. The implications become universe-shattering during a merger. As the stars spiral inward, their tidal distortions grow, stealing energy from their orbit and hastening the final collision. The specific way they deform dictates the ultimate fate of the cataclysm. Will the merger instantly form a black hole, or could it briefly create a more massive, unstable neutron star? The answer is written in the tides. When the LIGO and Virgo observatories detected the gravitational waves from a neutron star collision, the signal contained a unique fingerprint of this tidal deformability. By analyzing the ripples in space-time, scientists could measure how much each star was stretched just before they collided, placing the first direct constraints on the stiffness of neutron star matter from an event over 100 million light-years away. This gentle, persistent pull of gravity, acting over vast distances, does not need to tear a star apart to reveal its secrets. It merely needs to see how it bends, using the fabric of space itself as a diagnostic tool to uncover the stiffest truths hidden within a stellar corpse. But the ultimate fate of matter under pressure may be even stranger than we have dared to suppose. The 18th wonder is the strange star hypothesis, a theory proposing that the most massive neutron stars might not be made of neutrons at all. Instead, they could be strange stars, celestial objects composed almost entirely of a soup of fundamental particles, up quarks, down quarks, and most importantly, strange quarks. This strange matter is theorized to be the absolute most stable form of matter in the universe, more stable than even the iron that sits at the center of a periodic table. If this is true, then any chunk of neutron star matter that touches this state would instantly convert, releasing a phenomenal burst of energy. The surface of such a star would be unimaginably sharp and distinct, a boundary only a single atom thick, separating the vacuum of space from an unbroken ocean of pure quark matter. This radical transformation could be the engine behind some of the most powerful explosions we see, perhaps even certain types of short gamma-ray bursts. While the existence of strange stars remains one of the most speculative ideas in astrophysics, it forces a profound question upon us. What if the objects we have been calling neutron stars for decades are, in their most extreme forms, something entirely different? They would represent a state of existence so fundamental that it rewrites our understanding of stability itself, suggesting that at the heart of cosmic violence lies a perfect and strangely serene form of matter. Even in the aftermath of a stellar cataclysm, new worlds can be born. The 19th wonder is the existence of pulsar planets, entire worlds orbiting the radioactive hearts of dead stars. These were not the first planets we expected to find beyond our solar system, but they were among the very first ever confirmed. Their origin story is one of cosmic violence. A pulsar is typically born in a supernova, an event so powerful it should vaporize any existing planets. So how do new ones form? The leading theory points to a binary system where two stars once danced together. When one explodes, it can strip material from its companion or be surrounded by a disk of debris from the shattered remains. From this chaotic aftermath, a second generation of planets can coalesce, forming directly from the ashes of stellar destruction. These are not gentle terrestrial worlds. They orbit in an environment of pure fury, bathed in constant, lethal radiation from the pulsar's powerful beams and relentless stellar wind. A year on one of these planets might last only a few Earth days, a frantic dance around a cosmic tombstone. The very discovery of these worlds was a shock, forcing astronomers to expand their definition of where planets could exist. It demonstrated that the process of planet formation is astonishingly resilient, capable of occurring even under the most hostile conditions imaginable. This naturally leads to a profound, if unsettling, question. Could life ever gain a foothold in such a place, while the surface of such a planet would be sterilized by radiation? Speculation turns to the possibility of a thick, protective layer of ice or rock. A subsurface ocean warmed by tidal forces from the pulsar's fierce gravity could theoretically provide a shielded haven. While this remains a remote possibility, the mere existence of these worlds forces us to broaden our search for habitats in the cosmos. They are testament to the universe's relentless drive to create, even from the ruins of its most violent events, offering a glimpse of the most unexpected and hardy worlds in the galaxy. That steady cosmic heartbeat can sometimes skip, jolting forward in a fraction of a second. These pulsar glitches are the 20th wonder, tiny rotational hiccups that reveal a violent struggle deep within the star's structure. The phenomenon is a sudden, measurable speed up in the star's spin, a jump that can occur in mere minutes and then take months or years to settle back to its previous rhythm. The cause is a transfer of momentum on an epic scale. Picture the star's interior as two distinct components spinning at different rates. The outer crust and the inner layers of nuclear posta are solid and rigid, gradually slowing down over millennia as the pulsar's radiation bleeds away energy. But deep within, the neutron superfluid is a frictionless sea, and once it is set spinning, it wants to keep spinning forever. This creates a dramatic velocity difference between the superfluid core and the slowing crust. They are coupled together by billions of quantum vortices, those microscopic whirlpools pinned to the crystalline structure of the inner crust. A glitch is the moment this delicate arrangement breaks. It might be triggered by a starquake, a sudden fracture in the incredibly strong crust that releases pent-up strain. Or it could be the result of a collective unpinning, where a vast army of these quantum vortices suddenly breaks free from their anchors all at once. When this happens, they surge outward, carrying with them the immense rotational energy of the superfluid and delivering a powerful kick to the entire star. This is why we see that sudden jump in spin. Each glitch is a unique natural experiment. By meticulously recording the size of the jump, how quickly it happens, and how long the star takes to recover, astronomers can probe conditions that are otherwise completely inaccessible. A large, fast glitch suggests a different interior structure than a small, slow one. Monitoring these events across a population of pulsars helps scientists classify their internal dynamics, distinguishing between stars with softer cores and those with stiffer, more rigid interiors. These tiny anomalies are far more than just data points on a chart. They are the star's way of communicating its internal struggles, offering us a direct listen into the ongoing drama between a perfect quantum fluid and an unyielding solid crust, a conflict that shapes the very spin of a stellar corpse. A neutron star does not always live in isolation. When bound in a gravitational dance with a normal stellar companion, it can transform into a cosmic vampire, feeding on its partner to reignite its own furious energy. This is the 21st wonder, the phenomenon of X-ray binaries and accretion. The process begins with a simple, relentless pull. The neutron star's immense gravity begins to strip material away from the outer layers of its orbiting companion. But this stolen gas does not fall directly onto the surface. Instead, it forms a vast, swirling disk of superheated plasma that encircles the neutron star like a cosmic whirlpool, a structure known as an accretion disk. As this material spirals inward, dragged by friction and magnetic forces, It is compressed and heated to temperatures of millions of degrees. In this state of intense thermal fury, it does not glow in visible light, but erupts in a torrent of high-energy X-rays, making these binary systems some of the most luminous objects in the X-ray sky. This influx of new material does more than just create a brilliant beacon. It can literally rejuvenate the dead star. The incoming gas carries with it a tremendous amount of angular momentum, and as it crashes onto the surface, it transfers this spin energy to the neutron star. An old, slow pulsar, whose beams had long since faded into silence, can be spun up to a dizzying new rate, becoming a millisecond pulsar that rotates hundreds of times every second. We are witnessing stellar resurrection, a dead star being brought back to life by consuming its neighbor. For astronomers, these systems are priceless natural experiments. The rate of mass transfer, the brightness of the X-ray emission, and the changing spin of the pulsar all provide direct clues about the neutron star's magnetic field strength, its internal structure, and the complex physics of the accretion process itself. They reveal the final, dramatic chapters in the lives of binary stars, showing how a relationship that began billions of years ago can end in a display of brilliant, high-energy light, a testament to the transformative power of gravity itself. These stellar dynamos are natural engines for the universe's most energetic particles. The 22nd wonder reveals neutron stars as cosmic ray accelerators, the source of a mysterious rain of atomic nuclei that constantly bombards our planet. Particles themselves are familiar, protons and atomic nuclei stripped of their electrons, but their velocity is anything but ordinary. They fly across the galaxy at nearly the speed of light, carrying energies far beyond what any human-made collider can produce. For over a century, the origin of these ultra-high-energy cosmic rays has been one of astronomy's great puzzles, and the leading suspects are the intense environments around pulsars and within their vast, glowing nebulae. The mechanism is a natural version of a particle accelerator, but on an unimaginable scale. The pulsar's furious wind, a supersonic flow of charged particles, expands into the surrounding space, creating a powerful shock wave. As protons and ions cross this cosmic boundary, they are caught in a turbulent process and reflected back and forth, gaining a tremendous boost in energy with each pass. It is like rolling a marble between two rapidly approaching walls, with each collision propelling it faster and faster until it is ejected at a significant fraction of light speed. These neutron star accelerators do not merely create a local phenomenon. They contribute to the pervasive flux of cosmic rays that permeates our entire galaxy, shaping the energetic particle environment between the stars. This invisible rain has a subtle but real effect, contributing to the background radiation levels on Earth and even influencing cloud formation and atmospheric chemistry over long periods. By studying the specific signatures of particles thought to originate from these sources, scientists are slowly piecing together the journey of these cosmic messengers, tracing them back to some of the most violent and powerful engines in the cosmos. The most intimate secrets of a neutron star are written in its size. This 23rd wonder is the mass-radius relation, a simple-sounding concept that holds immense power. At its heart, it is a question of cosmic proportions. How large is an object that weighs 1.4 times the mass of our Sun? The answer is not a single number, but a curve, a fundamental relationship that directly confronts our theories. A large radius for a given mass points toward a soft and yielding interior, a core perhaps filled with exotic particles like hyperons or free quarks that compress more easily under pressure. A small, compact radius, however, signals a stiff and rigid heart, a core of pure neutrons or nuclear pasta that fiercely resists being squeezed any further. This is the equation of state made visible, a direct link between the star's fundamental properties and the deepest nature of its matter. We measure this relation not with a ruler but with light and gravity. X-ray telescopes observe the surfaces of neutron stars, some as they undergo violent thermonuclear explosions that reveal their true size, others in quiet states where their thermal glow can be carefully analyzed. Each observation adds a new data point to the cosmic graph. The revolutionary detections of gravitational waves from merging neutron stars provide another, even more direct method. The way spacetime ripples just before the collision is exquisitely sensitive to how much each star is deformed by its partner's gravity, a tidal effect that reveals its overall size and stiffness. Every new measurement, whether from an X-ray flash or a spacetime tremor, acts as a judge, ruling out entire families of theoretical models and bringing others into sharper focus. It is a slow, meticulous process of empirical discovery, testing our boldest ideas about matter against the cold, hard reality of the stars themselves. The profound insight here is that something as basic as a star's geometry, its simple mass and radius, can become a window into a realm of physics we can never visit, forcing the universe to confess what lies at the heart of its most perfect orbs. Even the most rigid crust cannot hold forever. The 24th wonder is neutron star seismology, the study of starquakes that ripple across these cosmic spheres. Just as our own planet shifts and groans with tectonic strain, the unyielding crust of a neutron star accumulates immense stress. This pressure comes from the slowing of its spin over millennia and the ferocious pull of its own magnetic fields, twisting the surface like a solid of unimaginable strength. When that strain finally exceeds its limit, the crust cracks, releasing a cataclysm of stored energy in a fraction of a second. This is a starquake, a seismic event that can be felt across the galaxy. The effects are dramatic and multifaceted. A major starquake can suddenly rearrange the star's magnetic field, leading to a powerful flare of X-rays or gamma rays, a burst of light that our telescopes can capture from millions of light years away. It can also trigger a pulsar glitch, that sudden speed up in spin, as the crustal shift unlocks the pinned quantum vortices within the superfluid core. But the true value of a starquake lies in the aftermath. After the initial fracture, the entire star begins to ring like a colossal bell, vibrating at specific frequencies determined by its internal structure. These oscillations are subtle, but they leave a tiny, repeating signature in the star's brightness or in the timing of its radio pulses. By carefully analyzing this stellar music, astronomers can perform astroseismology. Each vibration mode is a direct probe into a different layer of the star, from the iron surface down through the exotic nuclear poster and into the mysterious core. A star with a soft quark matter interior will ring with a different set of tones than one with a stiff neutron core. This fledgling science turns a catastrophic event into a powerful diagnostic tool, allowing us to listen to the inner workings of an object we can never hope to visit. The faint tremors traveling through that perfect sphere carry encoded messages about the ultimate nature of matter, revealing secrets that light alone could never show. This ultimate density frontier is where matter makes its final stand. The 25th and final wonder is the neutron star itself, a perfect boundary in the cosmos. It represents the absolute limit of density, a state of matter compressed to the very brink of collapse into a black hole. To study these objects is to push our knowledge of physics past its breaking point. Every observation forces us to confront the deepest questions in nuclear physics, particle physics, and general relativity all at once. They are natural laboratories, testing theories we could never hope to explore in any terrestrial experiment. The profound mysteries they guard, from the potential nature of dark matter to the elusive theory of quantum gravity, are the very forces driving decades of astronomical research. This final wonder encapsulates everything that makes neutron stars so captivating. They are not merely distant points of light. They are the living edge of our understanding, cosmic signposts that mark the boundary between the known and the utterly unknown. They beckon us to look deeper, to question further, and to accept that the universe's greatest secrets are often hidden in plain sight, locked within the hearts of these impossibly dense, spinning remnants. As we reflect on the incredible diversity of phenomena they host, from quantum vortices to starquakes, from pulsar planets to gravitational wave hums, one truth becomes beautifully clear. The journey to understand a neutron star is not a path to a single answer. It is an ongoing conversation with the universe itself, a reminder that the greatest wonders are those that continually challenge us to rethink everything we thought we knew. These stellar remnants are not cosmic hermits, but powerful engines shaping the galaxy around them. Each neutron star merger is a crucible of creation, forging the universe's heaviest elements in its violent embrace. The gold in a wedding ring, the platinum in a catalytic converter, even the uranium that powers nuclear reactors, all were likely born in the spectacular collisions of these incredibly dense objects. They seed the interstellar medium with these precious materials, providing the raw ingredients for new stars, planets, and perhaps even life itself. Their relentless particle winds and intense radiation carve out vast bubbles in surrounding gas clouds, triggering new waves of star formation and altering the chemical evolution of entire galactic neighborhoods. To truly understand the life cycle of the cosmos, we must first understand the profound influence of these seemingly small, silent objects. The next generation of observatories is poised to unveil their deepest secrets. The Square Kilometer Array, a radio telescope of unprecedented sensitivity, will listen to the faintest whispers of thousands of pulsars, mapping the galactic gravitational wave background with exquisite precision. Future space-based gravitational wave detectors will hear the birth cries of neutron stars from within their supernova cocoons and capture the final, frantic moments of mergers with stunning clarity. These missions will transform neutron stars from distant points of light into detailed, three-dimensional laboratories. They will test the very limits of general relativity, probe the nature of dark matter, and perhaps even witness the direct formation of a black hole from a collapsing star. Every new piece of data challenges our existing models, forcing us to rewrite textbooks and reconsider our most fundamental assumptions about matter, space, and time. The story of the neutron star is far from over. It is a narrative still being written across the cosmos, and with every observation, we are learning to read another line. From superfluid cores to quantum vortices, these 25 wonders reveal a universe of extreme physics. Each one serves as a cosmic guidepost, pointing toward a deeper understanding of reality's fundamental laws. Our journey through their hidden interiors has challenged our most basic assumptions, showing us that matter can exist in states beyond our wildest imagination, and that space itself is a dynamic fabric, constantly stretched and squeezed by these incredible objects. These stellar remnants are more than just distant points of light.